Okay, let's get back to the lecture. We have seen the quicksort algorithm. Let's try to analyze now its running time. So remember that the main quicksort algorithm had one main step which consisted of the partition algorithm. Afterwards, we had two recursive calls to quicksort. One of them was the middle index. Remember, doesn't exactly, may not correspond to the exact middle of the array. It actually denotes the index of the pivot element. Okay, so don't get confused with the name. The middle index, it denotes the index of the pivot element. So one recursive quicksort call will sort the array elements in between left and middle minus 1, and the next quicksort recursive call will sort the right part of the array consisting of indices in between indices middle plus 1 and right. This is the whole algorithm. Any guesses regarding the running time of this quicksort algorithm? Any guesses? Or how we should start analyzing the running time? Obviously, we should start analyzing the running time by going step by step, checking all the lines of the pseudocode. The first thing we need is the running time required by this partition algorithm. Assuming that partition works on an array of input size n, meaning that we have n elements in between left and right indices, what is the running time of the partition algorithm? Let's first decide on that. This is the partition algorithm. If the partition algorithm is working on an input of size n, meaning that A has n elements in between left and right, what is the running time of the pseudocode? Any guesses regarding this, regarding the running time of partition algorithm? Any guesses? So take a look at this code and also remember what the partition algorithm is doing on the array throughout its execution, and make a guess regarding its running time. What will be the running time? Can you all still hear me? Okay, so you can hear me. Uh, are there any guesses regarding the running time of the partition algorithm? Is it n? Is it n log n, n square, 2 to the n? What is it? So no guesses regarding the running time? What is the running time of these two lines of code? So I make an assignment, pivot is equal to a left, L is equal to left, R is equal to right. What is the running time of these two lines of code? constant running time, because in these two lines of code we do a constant number of operations, a constant number of, let's say, assignment operation, which is a primitive operation. Okay, let's check these two lines of code, the last two lines of code. What is the running time for the last? So the first part, this part, is just constant. We can denote constant with big O1. Note that all the time we denote the constant running time with theta 1 or big O1. The last one is the same, yes, because again we have one assignment and just a swap statement, which basically consists of three assignment statements. We keep a temporary variable, assign temporary variable to be equal to a left, and then we assign a middle to be equal to a left, and finally reassign temp back to a left. So three or four assignment statements, since we do a constant number of primitive operations, the assignment operations. Again, this part is big O1, constant running time. So, which means that the most important part to analyze is this main while loop. Can anybody see what the running time of this while loop is? Of the whole while loop? If we have n elements, if the partition algorithm is working on an array consisting of n elements, what is the running time of this whole while loop? Basically, what is the running time required by the code in this box? So Vladislav guesses that it might be n. Any other guesses? N square. There are two guesses of n square. Anything else? So why is it n square? Let's ask Emir first, for instance. Emir, why do you think it might be n square? If you can turn on your microphone and speak, that could be easier. So Emir, why do you guess that the running time of this piece of code inside the red box is n square?
Hocam,
Yes, I can hear you.
okay. First while loop, AL less or equal to the pivot, something like this is
Oh, this
going,
inside, okay.
yes, middle of the array, A.
What did you say about this first while loop?
It's going for searching pivot for less than or equal to AL, and L is less or equal to the right. So it's going for, if we have n elements in array, isn't it going for n over 2 elements?
Mm-hmm.
Same for the other.
The same is true for this one, you say?
Yeah.
So you're saying that this while loop might require n running time, because this is our, let's say this is our input array. We start L in here, but then we move L all the way to the end, which means that it processes, or at least it accesses maybe n elements. So this while loop, in the worst case, may repeat n times.
Yes.
The same might be true for this one. This might repeat for, in the worst case, it might repeat n times. And how did you arrive at n square? Can you still hear me, Emir? Can everybody hear me? Is there any problem with my internet connection? No, I couldn't hear the last part of your conversation, Emir. So you said that this first while loop, in the worst case, L starts here. This is L, and then we keep on moving L towards right. It might be the case that this first while loop may require n time. That's what you said. Same might be true for the second while loop. But how do you arrive at n square? You may arrive at n square by checking this outer while loop, saying that there's another while loop outside, which maybe we repeat n times. And since inside we have some statements that require n time, and the while loop we may repeat n times, that's why the running time is n square. Is that true? Is that the basis of your guess? Okay, so this is one idea, but while analyzing algorithms, we should be a bit careful. So it might be tempting. So whenever you see some, let's say, while statement or for, it could be for loop as well, some while statement, and then inside we have another while loop, and inside we have some statements in here. So it is tempting to check the running time of this inner loop and check how many times we repeat this outer while loop and then multiply them to come up with the running time. But in some cases we have to be a bit more careful, because it could be the case that even though we repeat this while loop in the worst case, we might repeat this n times. It could be the case that when we repeat this one n times, this part is not repeated n times. Okay, so we should do a bit more careful analysis. How can we do that type of a more careful analysis for the pseudocode inside the red box? Can you all still hear me? Do you all still follow? Okay, so if we do a more careful analysis, we will see that actually the running time is not n squared. Well, it is upper bounded by n squared, but that analysis, if you make a more careful analysis, that the running time is actually less than n squared. We will see that the running time of this red box will be n, will be theta n. Can anybody see why? Can anybody see why the running time of the pseudocode in this red box is actually theta of n? Somebody actually had a guess regarding theta n. I think it was Vladislav. So Vladislav, can you explain to us why this pseudocode inside the red box requires theta n running time rather than n squared?
I guess because we are like going through array one time, and sometimes like we stop to swap it. They're like swap is like constant, not constant or constant.
Constant. It is constant, yes.
While loop is n, and inner while loop is like also constant, I guess, or I haven't just heard, like I just guess.
While loop So we cannot say the while loop is constant. So yeah, you have a point. So let's try to explain it from another viewpoint. So rather than blindly checking, we have while loop, and then this is n, this is n, and then multiply that. Let's try to see what exactly the piece of code is doing throughout its operations, and from that let's try to find out its running time. So we initially start L pointing to the leftmost position, R pointing to the rightmost position. Let's say that, so this inner while loop will move L pointer to the left until it stops. Let's say it has, starting from the beginning, it has stopped at this position. How much running time have we spent, have this piece of code in the red box have spent up until now? So check the element under L, it is less than or equal to pivot, increment L. Check the element under L, it is less than or equal to pivot, increment L, and so on until L stops at this position, let's say, where we have found some element greater than pivot. Okay, L has stopped here. Up until now, what is the running time that is spent by the algorithm? The running time spent by the algorithm up until now is proportional to the number of elements we have seen so far, because for each one all we do is just some comparison and some increment operation, which both of them are constant, which means that this while loop until its stopping point will spend time proportional to the number of elements it has seen so far. If there were k elements in here, it will spend time theta k, k1 let's call. For R, for the second while loop, it is the same thing. It will move on towards left, it will stop at the position, R will move to the left, and it will stop at the position when it finds an element smaller than or equal to pivot. And let's see how much time our algorithm has spent up until now for this while loop. Again, it is proportional to the number of elements it has seen so far, k2. Okay, this is the we spend big O k2, where k2 represents the number of elements in here that we have seen so far. That's the running time spent by this second while loop until while loop stops. Once they stop, we do a swap of these two elements, and swap is just a constant time. Okay, meaning that once we finish one iteration of this outer while loop, we spend time proportional to the number of elements we have seen so far. Okay, which is k1 plus k2. And we come back to the outer while loop, we repeat the same thing. So L will move left, R will move right, and then we will spend however many elements we have seen here and however many elements we have seen here, and then we will add these to our running time. At the end, we will see that we have added in terms of running time spent by these while loops, we have added some number proportional to the number of all the elements inside the array. Okay, which means that the running time is just linear. Okay, or if you want to think of in terms of another way of thinking in terms of the running time is, now this array A has n elements. how much time does this piece of code in the red box spend per element? So for instance, I take a look at I pick an arbitrary element inside the array. What are the operations executed on this array? How much time is spent for this element of the array? For this element of the array, if it is under L, if it has been accessed under L, and if it is true that it is smaller than or equal to pivot, we will just move our left pointer to the right, which means that for this element overall, the whole while loop, we have spent only constant time. Otherwise, maybe we have done a swap which is also constant time, which means that this pseudocode inside the red box is simply spending constant time per element inside the array. And if we have n elements in the array, and for each one, since we spend constant time, the running time will be theta n. Is this discussion clear? Is this discussion regarding the running time of this red box clear, that it requires theta n running time? Should we repeat any part of this running time analysis? You can think of it as follows. So let's say that if I had an array and if I had a single pointer and I was just, for each element, I'm checking something, some constant amount of time, and I'm going to the next element, some constant amount of time, and I'm going to the next element, some constant amount of time on the current element, and I go on to the next. If I had n elements, this would be theta n, because I'm doing a kind of a linearly going over all the elements of the array, and for each element I'm spending big O1 constant time. So the overall running time of such an algorithm would be theta n. This is also quite similar. Instead of just one pointer, we now have two pointers, L and R. So L will sweep towards right, and R will sweep towards left. This is no different from sweeping all the way from left to the right, because when these two pointers meet, we stop our operations. We don't continually do any further sweeps. Okay? Up until L and R, the pointers L and R meet, the time spent for the L pointers will be similar to this linear sweep towards right, which is number of elements here, and the time spent within all the second while loops will be also proportional to the number of elements in this right subarray. Okay, overall, the running time of the whole while loop will be n, will be linear. Is this part clear? Is this part regarding the running time analysis of this piece of code clear? Is it only clear for Vladislav, or everybody else also understand why the running time is theta n? So only Emir has replied. So let's see. Enes, if you're still there, is it clear for you as well? Is Enes here? Are you still listening, Enes? How about Metehan? Are you still listening to the lecture? Are you still following? Metehan, are you still following the lecture? So I guess Enes has stopped attending, and also same for Metehan. Asena, is it clear for you? Okay, so for the people who haven't answered, Enes and Metehan, you don't have to attend the classes if you are not interested. So uh, just don't log into the Teams application and then just don't leave. That's not the way to attend a lecture. I don't know if you're still hearing me, probably not. But anyway, so if for the rest of you as well, if you're not interested in listening to the lecture, just don't pretend to be attending the lecture by just logging in. Okay, let's continue. We have seen that the running time of the partition algorithm, then overall, so this was constant, the part in the red box was theta n, which means that the running time of the partition algorithm will be theta n overall. Now let's get back to the running time analysis of our quicksort algorithm. Now we know that the partition requires theta n running time. What can we say about the running time of the quicksort algorithm then? Any ideas regarding this? Regarding the running time of the quicksort algorithm? We know that partition requires theta n time. Any guesses from anyone? N divided by 2. Beril, we are talking about the whole running time of the quicksort algorithm. Okay, so we know that a single call to partition will require n time, but then we make a recursive call to quicksort on some portion of the array. We make another call to quicksort recursively on another portion of the array. We have to account for the running time spent in these recursive calls as well, which means that remember what we needed to do while analyzing time of algorithm. We should write a recurrence T of n that describes the running time of our recursive algorithm. Quicksort is recursive because it's making two recursive calls inside the algorithm. So we need to describe its running time as a recurrence relation as well. Can anybody tell me how to write the recurrence relation Tn, which describes the running time of quicksort? We know that partition will require theta n, so somewhere we should write plus theta of n, and then in here I need to write some terms that will describe the running time spent for this first recursive call and the running time spent for the second recursive call. I need to write down these ones, add these ones to theta n to describe a running time, to describe the recurrence which denotes the running time of quicksorts. What terms should I add in here to describe the running time of these two recursive calls? So 2 times t of n divided by 2, Asena has suggested. T of, I'm guessing that t of n divided by 2 for the first recursive call, t of n divided by 2 for the second recursive call. Is that true? Okay, this is good. So at least you have seen that we need to describe the running time spent for these recursive calls using the t term, because t of n denotes the running time of quicksort on an input of size n. If that is the case, this is also a quicksort call, so we will denote its running time with t as well. But the only detail, Asena, is that this part denotes us the size of the array that this recursive call will work on. If the size of this subarray that quicksort will work on was n divided by 2, or in other words, middle was actually exactly the middle of the array, then you're right. This would be t of n divided by 2. This would be t of n divided by 2. However, remember that the partition algorithm partitions the input array such that once partition is finished, it will also return a middle index. But this middle index, let me just write down m for this middle index. Remember that this middle index m doesn't correspond to the exact middle of the array. It corresponds to the position where the pivot element belongs to. So for instance, let's see our example. In this example, for instance, we have how many elements? 3, 6, 9, 12, 15, and 16. We have 16 elements in this array. The exact middle is, let's say, this position, exactly at index 8. However, when we use the middle index, we don't mean the exact middle. We mean the index of the position where the pivot element belongs to. So our pivot in this case is 6, and 6 in this whole array is the 6th smallest element. So this index is 6 as well. In this case, our value for m is 6, the index of the middle of the pivot value. So this m might be anything. If my pivot for this whole array was, for instance, 15, then the middle index would turn out to be towards the end. That would be the middle pointer that is output by the partition. So, which means that the number of elements that this quicksort call and this quicksort call works on depends exactly on the value of this index m, this middle index, which actually is the correct position of the pivot value. Okay, so let's write down this recurrence by parameterizing that middle index with m. So if m is the index of the pivot value, this means that after the partition, the array is divided into two parts. One of them consisting of m elements, the other part consisting of n minus m elements. So, which means that this initial quicksort, if there are m elements here, its running time will be t of m plus the running time of the second quicksort call will be, since there are in the right subarray, since we have n minus m many elements, its running time will be t of n minus m. Okay, so partition requires theta n running time, assuming that after partition the index of the pivot element is found to be m. This first quicksort call will require t of m running time, because that is the size of the input that this quicksort will work on, and the running time of the second quicksort, of the second recursive quicksort call, will be t of n minus m, because that is the size of the input array that the second quicksort call will work on. Okay. Now, Asena, as you have suggested, if this m turns out to be the exact middle of the array, then we will have t of n divided by 2, t of n divided by 2, or in other words, 2 times t of n divided by 2 plus theta of n. But this is just one case. It only happens when the pivot element that we start with exactly belongs to the median of the array, is exactly in the middle of the array. But that might not be the case for every pivot value that we try. Is this clear? Is this clear why we have written occurrence relation describing the running time of the quicksort algorithm in this way? Any questions about this? Now, looking at, is this clear, Asena? Why we haven't written down t of n divided by 2 for each one? Is this clear? Okay, now looking at this, just by looking at this, it doesn't tell us anything. It doesn't tell us how big this running time is. And a second important thing is that this Tn will actually, how big it is will be very much dependent on the value of m. Okay, which means that just the same way that we have done with the insertion sort, it could be the case that this Tn is a slowly growing function depending on value of m. Maybe m is poorly chosen so that this Tn is a large function. Both of them are possible. Okay. This means that we need to do separate analysis for the running time. We need to do first a best case analysis where we try to write down n, assuming the best scenario possible for this value of m, so that Tn is as small as possible of quicksort. But also we need to do a worst case analysis where we try to find out what could be the worst possible value for m such that this Tn is as large as possible. Let's first start with the best case. What could be the smallest function Tn? So, or in other words, if to what value setting m would make Tn as small as possible? So let's say that I have done the partition, and the partition, after the partition, I have a very imbalanced partitioning. So that, let's say this is where the pivot element belongs to, this is my mid index, so that I have partitioned the array into two, one part very small, one part very big. Would this be a good partitioning? Would this give us a good running time? So doing unbalanced, having unbalanced partitions is one extreme. Okay, so this is, let's say, unbalanced partitions, where after doing the partition we find out that the middle index is close to one of the ends. In this case it's close to the left end, for instance, so that we have a very few number of elements on the left array, very large number of elements in the right array. And remember that quicksort will recursively work on this part and it will recursively work on this part. This is the figure of an unbalanced partition. Remember that while working on this array, we will do the same thing. Again, do a partition, in which case it might repeat the same unbalanced partition, so that this is the mid index, it partitions this left array and this right subarray. So we can, on the one extreme, we can assume that always unbalanced partitions happen. On the other, let's try to draw another figure for the other extreme. We can have balanced partitions, so that right after this partition operation we find out that the pivot index belongs to almost to the middle of the array, so that for the left subarray where we execute this first recursive call, we have almost n divided by 2 elements. For the right subarray, it's the same, almost n divided by 2 elements, and we will work on recursively for the left subarray. And while we do the partition for the left subarray, we can assume same thing happens, that we have a balanced division, the balanced partition, so that the pivot element is almost in the middle, left part has almost the same size as the right part. Same is true for this one. This would be an example figure for balanced partitionings. Note that we have no choice over having a balanced partition or unbalanced partition. It totally depends on the input that is given to us. But while analyzing, we can decide on whether this would be a good case scenario in terms of running time, or having unbalanced partitions would be a good scenario. Any ideas in terms of this running time that we have written down in here? Do you think that having balanced partitions is a good partition for running time, or having unbalanced partitions? In other words, if I have balanced partitions all the time, would I have the best case scenario? Or if I have unbalanced partitions all the time, I would have the best case scenario. Which one would give us the best case scenario? When we say best case scenario, obviously we mean the smallest possible running time. So Asena guesses that it might be balanced. Yes, that is true. If we have balanced partitions, then the running time of the quicksort algorithm is as small as possible. Let's try to analyze the running time for such a scenario. In such a scenario, note that since the division is balanced, m will be equal to n divided by 2. This one, n minus m, will also be n divided by 2. So our running time will be denoted with this recurrence. 2 times t of n divided by 2 plus theta of n. And you must remember this recurrence from our previous classes. This is exactly the recurrence that we have used to describe the running time of the merge sort algorithm. And you can use the master theorem, the master method, to find the theta bound for this recurrence t of n, and you will see that it evaluates to theta of n log n. So if all the partitions, also we are counting the partitions that happen within the recursive calls as well. If all the partitions throughout the quicksort algorithm's execution do balanced partitions such that at each partition the array is divided into 2 equal halves, then the running time of the quicksort algorithm is theta n log n. We will see that this is actually the best case scenario for the quicksort algorithm, because having unbalanced partitions, we will see having unbalanced partitions is actually quite bad for the quicksort algorithm. How can we denote the running time Tn, this general running time Tn of quicksort for unbalanced partitions? What would be the worst case scenario for unbalanced partitions? The worst one would be, for instance, this is after the partition, let's say our algorithm is quite unlucky so that the pivot belongs to the leftmost element such that the middle index m is at the leftmost position. When can this happen? If the pivot element is the smallest element of all. So for instance, for this element, if pivot was chosen to be 1 rather than 6, let's say 1 was here, the leftmost element. Since the leftmost element is chosen as the pivot, pivot would be 1. Now after the partition, pivot would be here. The position of the middle index would exactly be pointing to the leftmost element, which means that this t of m would simply be, so this would translate into t of n is equal to, for the left part of the array we don't have anything, so we can just, let's write down only t of 1, which is 1. We don't even have to write this part, plus the right subarray, the size of the right subarray where the second recursive quicksort will work on is t of n minus 1. Let me not write down this one because this is just constant, plus the theta n running time we spent for the partition. So in the worst case, if the partition divides the whole array in a very unbalanced way, such that in the left no element remains and all the elements are in the right subarray, so all n minus 1 elements are in the right subarray, then this is the recurrence. Does anybody remember this recurrence from our previous classes? T of n is equal to t of n minus 1 plus theta n. Does this recurrence look familiar to you? T of n equals t of n minus 1 plus theta of n. Is this familiar? Anybody remembers this from our previous lectures? Remember that this was the running time or the recurrence relation that we have written down to describe the running time for the worst case analysis of insertion sort. And if you try to do expansions, if you try to guess T of n, a bound for T of n using expansions, which is similar to a recursion tree, you will see that T of n is, in this case, is actually theta of n squared, which was also the worst case running time of insertion sort as well. So if we summarize, we see that quick sort algorithm for the best case will have a running time of theta n log n. This happens when all the partitions are balanced. And the worst case running time of quick sort is theta n squared. This happens when all the partitions are unbalanced. Any questions about this? Any questions regarding the worst case and the best case running time analysis of the quick sort algorithm? Is the running time analysis clear? For the best case analysis, we consider the best case partitioning possible for all the quicksort calls, and we come up with this recurrence, which is theta n log n. And for the worst case analysis, we see that unbalanced partitions are the worst case for the quicksort, and we come up with this recurrence to describe its worst case running time, which evaluates to theta n squared. So in the worst case, running time is theta n squared, and in the best case, running time is theta n log n. The best case running time of quicksort is exactly the same as the running time of merge sort and heap sort, both of which had a running time of theta n log n, and its worst case running time is the same as the worst case running time of insertion sort. So if you don't have any further questions regarding this, we will actually have one more type of analysis, running time analysis for quicksort, which we will call average case running time. But since we don't have any time to discuss it, we will leave it for discussion next week. So next week we will continue with the analysis of quicksort. We have seen best case analysis, worst case analysis, and next week in the first lecture we will talk about average case analysis of this quicksort algorithm. So if you don't have any further questions, let's stop here then.